Thanks, John, and thank you very much. As you heard, I'm going to give a brief talk, a pivot, on data-driven visualization of drug interactions. Drug interactions, adverse drug events, are pretty simple. You are taking two or more drugs, a bad thing happens, and it was unexpected. That is the definition of an adverse drug event. About 1 million deaths or injuries per year in the US are attributed to adverse drug events. Some fraction of them are unknown. We didn't understand before those drugs were prescribed together that these bad things might happen. Clinical trials fundamentally can't cover the entire reaction population. Not all of the results that you will see in large-scale deployment are visible from pure trials. There are, though, sites where the Federal Drug Administration and the World Health Organization track these things. Doctors and patients can go online and report these events when they happen. It's possible for a data scientist to go download that data and take a look at it. We can explore that data using big data analysis tools in order to understand adverse drug events. But it ain't easy. There are a number of difficulties. First and foremost, the sample is biased, right? You only see reported events. When things go well, no one reports a good outcome. When things go badly, only some people report a bad outcome. It's also important to remember, and this is always important when we're looking at data, the fact that you see correlation in results doesn't imply anything about causation. Could be coincidence, could be anything at all. Anything at all. And in addition, in order to analyze these drug events well, you've got to use some pretty sophisticated tools. What we've used in the visualization I'm going to show you is something called Gamma-Poisson Shrinkage Estimator. It's a statistical model that tries to understand the significance of the interactions that you're seeing. It's very, very tough to solve completely. We do use some simplifications in exploring that model. Those aren't the tough thing, though. The tough thing is actually counting. It turns out that there aren't that many events you need to look at, but there is a problem. When you consider all the drug interactions, when you look at all of the variables attached to patients, the numbers get big in a hurry, from 1 million reports to about 360 million buckets that we need to look at. We have in the past used sampling or filtering in order to reduce that population to a manageable number. That is not the way of a data scientist. We unfurled something called Hadoop, a tool, MapReduce, that allows us to examine this data in detail. We gathered together 20 MapReduce jobs, digested the data, used another data analysis tool called R to explore it, and then visualized the results. And I want to show you the first visualization. This is a drug-drug interaction graph. The circles are the number of interactions that a particular drug was involved in. The edges, the thickness of the edges, depends on the results of the Gaussian Poisson estimator that I described to you earlier. Basically, how sure are we that these interactions are real? And you can see clusters of drugs that are prescribed together on this graph. This graph, by the way, was rendered by an open source tool called Gephi. You drill in a little bit, you see down here, here's an HIV cluster. Unsurprising that these drugs interact with one another. They're prescribed a lot, and they've got a bunch of side effects. Up here, we see breast cancer and prostate cancer drug interactions. Again, unsurprising, prescribed together all the time. But if you know graphs, what's really interesting isn't individual clusters, it's connectivity. So let's look at connections between the graphs. Here we see a drug, Arixtra, that is a blood thinner that interacts with a drug called Loxonin, an anti-inflammatory drug like ibuprofen. Loxonin also interacts with a drug called tacopron. This is attached to another cluster. By looking at these connections on the graph, we can draw a few conclusions. First of all, visually we can see that Loxonin is different from a number of other AIDs. It doesn't interact with everything. Perhaps we could prescribe another. In addition, it is the case that we might be able to deduce the metabolic pathway, the way that drugs interact, by looking at this graph. The fact that Loxonin interacts with two clusters might give us a clue as to how those drugs actually interfere with metabolic pathways. This is just visualization. This is not science, but this can suggest to medical researchers promising areas of investigation. I've got Summary slide here. These slides will be posted online if you want to explore the data yourself. I want to thank Josh Wills, the Director of Data Science at Cloudera, for putting this together. Thank you very much.
Thank you, Mike. Thank you very much for that.
Actually, let me grab my...
See you now.